So we'll now again relook the process of transformation of the impedance plane to the reflection coefficient plane. As I told earlier, we are using this parametric reflection coefficient equation that helps to transform the impedance domain to the reflection coefficient domain, and this is the equation for R and this is the equation for X. What it does, as I mentioned earlier, it transforms point by point. So now let's go to the transformation of R equal to 0. Now R equal to 0 means it is the vertical line in Rx plane. Okay, R equal to 0 is a vertical line in Rx plane which actually accounts for all possible values of imaginary impedance. Okay, that is X. So when I substitute R equal to 0 in this equation, it gives me a equation like this. Gamma R square plus gamma I square is equal to 1. Now this equation is very similar to the equation of a circle with radius 1 and center at 0, 0. So if I just go to the Smith chart, see, this is it actually represents the outer circle with center at 0, 0. So this can be the origin. Okay, I have not yet defined this as 1 or I have not defined that as 0.5 or any circles. Don't go by those values right now. So this becomes a circle. It becomes a circle with radius 1 and center at 0, 0. So that 0, 0 is gamma R is equal to 0, gamma I is equal to 0. Now whether it will be circles or whether it will be ellipse, because as you can see in the equation, you have two different parameters, gamma R and gamma I. So they can have unequal values. So whether it will be a circle or whether it will be an ellipse with major and minor axis, that needs to be seen over next discussion. So to begin with, when R equal to 0 for all different values of X, it appears to be a circle with outer circle with radius center at 0, 0 and radius 1. Next, R equal to 1. Okay, now remember we are transforming Rx to gamma R and gamma I domain or U and V domain as I have shown in the earlier slide. So here R equal to 1, if I substitute R equal to 1, then you have a circle of this form, this equation of this form. Gamma R minus 1 by 2 the whole square plus gamma I square is equal to 1 by 2 square. Now what it represents? Again, it represents the equation of a circle with center at 1 by 2, 0. With center at 1 by 2, 0 and radius 1 by 2. So if I just go to this Smith chart again I am telling you again, don't read any values right now, just read this as a circle in gamma R and gamma I plane. So this is the center we have drawn earlier outer circle. Now next, when R equal to 1, where is the center shifted to? 1 by 2, 0, right? So if I consider this as a real axis and this as an imaginary axis, I have shown you earlier, then the center has shifted over here and radius is 1 by 2. So this becomes my circle for R equal to 1 with center at 1 by 2, 0 and radius 1 by 2. That's why this I have represented as 1 in the Smith chart, because this is a circle for R equal to 1. So you can see that the center of the Smith chart has slowly shifted towards the right side. Remember, center of the Smith chart has slowly shifted towards the right side. This is my gamma I plane, this is my gamma R plane. So here I am plotting the center point and drawing R equal to 1 circle with radius 1 by 2 and center at 1 by 2, 0. So this is the circle for R equal to 1. Next, R equal to infinity. If I substitute R equal to infinity in this equation, how the equation looks like? For resolving this, just divide numerator and denominator by R. Okay, just divide numerator and denominator by R, you will get this equation, gamma R square minus 1. Okay, and then gamma I square is equal to 0. So what it means, this is again the equation of a circle with center at 1, 0 but radius 0. So it is basically a point at 1, 0. It is basically a point. What the circle represents? It is a circle with center at 1, 0 with radius 0. So it is basically a point located at this point. Why? Because this radius is equal to 1. So the center of the circle resides over here and radius is 0 means it is a point. So r equal to infinity for all values of x, remember r is equal to infinity for all values of x, it becomes a point. So short circuit or r equal to 0 was basically a outer circle, then r equal to 1 is this circle, the center gradually shifts towards right, and r equal to infinity becomes a point. Now likewise you can do this plotting for r equal to all other values. What you will see, like I have taken the example of r0, 1 and infinity. If I take in between values, you will observe that the center of the circle will move from left to right. You will observe that the center of the circle will move from left to right and the corresponding radius will go on decreasing from 1 to 0. So this is basically because here for 0.1 circle, the center of the circle will come somewhere here and the radius the remaining value which is there. So while drawing, when we are transforming different r vertical domains, I will show that to you pictorially also. While transforming all vertical lines, that is the r lines, I am basically transforming them into the circles in the gamma r and gamma I domain. So vertical lines in the impedance domain becomes the circle. They are not concentric circle because their center is continuously changing. So don't consider them as a concentric circle. They are the circle whose centers are continuously changing. So that's why this is a 0.1 circle, 0.2, 0.3 and so on. And then the infinity. And again note, these are all normalized r. R is what? R upon Z, not what we are plotting. We are not plotting the absolute value over here. In those equations also, it is basically the R upon Z naught value which is being considered, not the absolute value. Okay, so we have transformed complete R domain circles, or we have transformed complete R vertical lines in R plus Jx circle. Now similarly, let's do this exercise for a X plane, that is the reactive part. Okay, let's do this exercise for reactive part. So x is what? R plus or minus jx. Reactive part we will now transform. Now what they represent? They represent the vertical lines. Okay, they represent the vertical lines in the impedance domain. So what we have done, we just go back. What we have done, we have basically, this is the impedance domain. So we have transformed all these R lines. Now we will transform all these constant X lines, that is constant reactance lines, we are going to transform. So now let's go to that equation. We will be using this equation now to transform. Now let's go one by one. Let's take X as 1. Let's select X at 1. If you substitute that into this equation, okay, if you substitute that into this equation, for X is equal to 1, that is 1 J1 value. Okay, it gives me an equation which is something like this. It gives me an equation which is something like this. Now what it says, in gamma R and gamma I domain, this represents the equation of a circle with center at 1, 1. Remember, in gamma R and gamma I domain, this represents the equation of a circle with center at 1, 1 and radius 1. Okay, with radius 1. Now what it means, we just go to the Smith chart here. This is basically a Smith chart. This is the gamma R axis. This is the gamma I axis. So a center of this circle will reside somewhere here. Okay, and then that circle needs to be drawn for area lying under our gamma mod gamma less than 1. So remember, reflection coefficient has to be less than 1. So we are going to consider the locus of that circle lying inside mod gamma less than 1. Because here mod gamma, if you take, it will be more than 1. It is underscore r square plus x square, or underscore under root gamma r square plus gamma I square. Okay, so that mod value will be more than 1. So we need to select the section or the portion of that particular circle for x equal to 1, which is lying inside mod gamma less than 1. So in that regard, being the center over here, only this section of that circle arc, 90-degree arc of that circle will reside inside that gamma less than 1 circle. So for x is equal to 1, it becomes an arc. Okay, for x is equal to 1, the section, the portion of that locus circle which resides inside the gamma r less than 1 area is becoming the arc. Okay, understand this point very precisely again. I'll try to explain pictorially also. See, this is my gamma r and gamma I domain. So we have drawn initially this circle. So this circle was drawn, and consecutively we have drawn all other circles. So we have transformed all real part into the gamma domain. Now what we are doing, we are transforming imaginary part. So for x is equal to 1, we get a point over here. But remember, at this point, mod gamma is going to be more than 1. And we are interested only in gamma less than 1 because those are the limits. Remember, limit of gamma is less than or equal to 1. We cannot exceed the value of gamma while doing a reflection coefficient calculations because gamma more than 1 has a different implications. Those we'll see later. So here gamma needs to be less than or equal to 1. So this is basically for this particular point, when the center is located at that point, how the circle or how the locus for that x will appear. It will appear like a circle which is lying outside. It will appear like a circle lying outside. So we need to only check the area of that circle which is residing inside. We need to only pick up the values of those x which will give me the value of gamma r and gamma I residing inside that circle. So that's why x is equal to 1 becomes r inside the gamma r and gamma r circle. So this is basically r which is plotted. So this is the principle behind it. Okay. Likewise, you will use different values of x, and then what you will see different at points, those centers will be located. We'll just go to a couple of more values, how the transformation happens. Okay. So now let's go to x is equal to minus 1. When x is equal to minus 1, if you substitute into this equation over here, you will get an equation similar like this. Gamma r minus 1 the whole square plus gamma I plus 1 the whole square. Remember, this is the typo error over here. This is 1 basically. Gamma r minus 1 the whole square plus gamma I plus 1 the whole square is equal to 1. Now what it indicates? It indicates now the center located at minus 1, sorry, 1 comma minus 1. The center is now being located at 1 comma minus 1. And the locus for that particular value of x will now appear like this. This will be that circle which is lying outside. Okay, minus 1 comma 1 comma minus 1. Earlier it was 1 comma 1. Now 1 comma minus 1. So we are going to be interested only in the portion of that circle which is residing inside gamma less than or equal to 1. Mod gamma less than or equal to 1. Hence, x is equal to minus 1 becomes the arc. Hence, x is equal to minus 1 becomes arc on the bottom side inside a Smith chart for mod gamma less than 1. Or to be very precise, for mod r or mod I less than 1, we are going to only see that much section inside the circle over here. Remember, I have not defined that as a complete Smith chart yet because we are plotting, we are transforming different r, different x curves. So this is the locus what I am generating, then I will call that as a Smith chart where it has a unique one-to-one mapping. That also we will discuss further. So this is the point, this is the locus for x is equal to minus 1 and this is the locus for x is equal to plus 1. Now similarly, you can transform all those values. So what will happen, in fact, you can just take for example, what will happen for x is equal to 1 by 2. Let's see what will happen for x is equal to 1 by 2. Just substitute in this equation. Okay, this will remain the same, gamma r minus 1 the whole square, so no change in that. But if I substitute 1 by 2 over here, then what will happen? It will become gamma r minus 1 the whole square plus gamma I minus 2 the whole square. Okay, the equation will look like this. Gamma, because here it is 1 upon x, so it will become 2, right? And then what will be this equation? 1 upon 2 the whole square. So it becomes 1 by 4. Now let's see how the circle gets plotted. So where is the center now? Gamma r, what was the equation? Gamma r minus 1 the whole square plus gamma r minus 2 the whole square is equal to 1 by 4. That was the equation what we obtained. So where the center had shifted now? Center had shifted over here. For that x is equal to 1 by 2, center had shifted over there. And what is the radius? What is the radius? It is only 1 by 4. So accordingly, you need to draw that circle and pick up that portion of the Smith chart. So I am drawing it for 1 by 2, right? So we'll just cross check again. The center here I am plotting it for x is equal to 1 by 2. So this becomes ulta, so it becomes 4. The correction over here, correction to be noted. Here I am saying x is equal to 1 by 2. So 1 by 2 means this becomes 2. So this also goes into the numerator. The equation is gamma r minus 1 the whole square plus gamma I plus minus 2 the whole square is equal to 4. That is the equation. Okay, that is the equation. So here this is 4. So where the center will lie? Center will lie somewhere here, and the radius of that circle is how much? 4 units now. The radius of that circle will be 4 units. So accordingly, while taking the 4 units, you need to draw that arc, and then what you will observe, it will have literally, it will have a arc which is encompassing that Smith chart from here. Okay, it will have a arc which is going to encompass the Smith chart like this. So this is the different arcs. This is how you are going to transform different arcs into the Smith chart. Okay, in fact you should be drawing, or you should be calculating, writing down the equations for different values of x, and then see how the center resides, and then accordingly draw the arc which resides inside the circle. Okay, so likewise you will see all such arcs will be transformed from the impedance domain to the reflection coefficient domain, and you develop a complete Smith chart over there. Okay. Now last part, let's see what happens if r is equal to x is equal to infinity. If x is equal to infinity, if you substitute that into the above equation, you will get the equation like this. Gamma r minus 1 the whole square plus infinity is equal to infinity. So this is basically a circle whose center is residing at 1 comma infinity with radius infinity. Again I am repeating, x is equal to 0, I am talking about 0, that is a short circuit condition. It is basically for that you need to substitute this, x is equal to 0 over here. Okay, so that is the x value is 0 over here. What you will get, gamma r minus 1 the whole square plus infinity is equal to infinity. So what it means, x is equal to 0, it is a circle whose center resides at 1 comma infinity and having a radius is equal to infinity. So what it means, inside the Smith chart, now just imagine the center is residing at 1 comma infinity. Infinity I cannot define, and the radius is infinity. So considering that infinite extent, the section of that particular arc which resides inside the Smith chart becomes a straight line. Okay, because see, when the radius is infinity, when the center is there at infinity, you cannot have any arc which is residing, we are having some particular curve, it becomes a straight line. Okay, when you have like what we said, always parallel lines meet at infinity, the same concept applies over here. So when you are having a center at infinity, radius is infinity, it basically represents a straight line inside gamma I and gamma r circle. So this becomes a real axis. Why? X is equal to 0 means no reactive part. So it becomes a real axis. That's why this particular thing is termed as a real axis for a Smith chart. So likewise, we have transformed all x and all r curves to gamma R and gamma I plane to draw the complete Smith chart. So now let's see how this procedure pictorially looks like. So this is basically the mapping of different R curves. So as I told you earlier, different impedance lines, different R lines are getting transformed into the circles. You can see they are not consecutive circle as I told earlier. The center gets shifted and they becomes a point ultimately when R is equal to infinity. So this is a drawing of R circle in the Smith chart. Then the mapping of X values. So you can see these are the different X which are getting transformed. As I told you earlier, like say earlier I have taken an example of 1 by 2. 1 by 3 example is there. The center of that will reside at 3 comma or 1 comma 3. So that section of that Smith chart which is residing inside, section of that curve which is residing inside gamma R and gamma I less than 1 is taken over here. So that becomes R. So all these horizontal reactance lines are getting transformed into the respective arcs inside a Smith chart, and then circles are getting vertical impedance resistance lines are getting transformed into the circles, not consecutive circles. So likewise, when I combine both the things, then you have this complete R plus or minus Jx domain getting transformed. So this becomes a complete Smith chart. Remember the boundaries as I have shown over here, gamma R and gamma I, boundaries are always less than 1. Boundaries are always less than or equal to 1. So this is the complete development of the Smith chart. So now this Smith chart will be used now later for different calculations. Likewise, we will be doing following experiments. We will be basically, or rather tutorials, we will first understand the procedure to locate the point on the Smith chart, then calculate the reflection coefficient because it is required in microwave analysis. Then we calculate the VSWR. Then we will calculate the input impedance of transmission line using Smith chart. Then we will do various impedance matching calculations. So we will use a lump as well as a distributed element. In lump element we will use the LC section matching, and in the distributed element we will use a transmission line matching, where we will have an open circuit stub or a short circuit stub connected in series or parallel. Then we will have the problem solving based on the T-pi network matching, as well as prior to that we will understand the admittance Smith chart as well as the admittance and impedance Smith chart together, because what we have developed here is an impedance Smith chart. So we will try to understand the similar admittance Smith chart and impedance and admittance Smith chart together. Okay, then we will solve a T-pi network. Okay, and in the end we will deal with a negative resistance Smith chart, because yet we have only transformed R plus Jx or R minus Jx domain. We have not rather dealt with minus R part. So later on we will also do a negative resistance Smith chart also. We will call that as a compressed Smith chart. So these are all the things what we are going to do in the next lectures using Smith chart. Thank you.